Hey everyone, and welcome to part 6.2 of our notes. This is we're going to talk about the electric current, okay, and get some of the basics in there and everything like that. So we just got done with statics, and now we're going to current. All right. Oh, there we go. Okay, so there's our assessment statements, if you will. All right. So the battery. All right, the battery is all about the storage of electrons and everything like that. And the idea of that there's a chemical reaction in here that is producing an electric kind of thing, which causes heat, the transfer of energy, and everything like that. So the best way we can think about this is the water analogy. Okay. Now they like to use a tank of water, like somebody doing work coming up the steps, putting water in here. This water has potential energy. Potential energy is converted to kinetic energy, which we've talked about in like the roller coaster problems. All right. And the wheel would be causing resistance or doing work and so forth and so on. That's kind of how people like to do it in physics. I also like to think about it just like playing with a hose out in the backyard in a water fight. And we'll kind of talk about this. And we should have talked about that in the bead lab that we've already done. So, a good way to think about it is the terms voltage, current, and resistance. Okay. Resistance is probably the easiest to understand. Like if something's resisting you, it's causing you to slow down or it's impeding you. So some people think of that as like rocks on a river. Okay. Current, you're familiar with the term current, all right, as in like the flow of something. So a lot of people like to think of current as flow. It is the flow, it is a rate. Current is a rate. And voltage, you've probably heard in the idea of PSI, like your car tires usually are somewhere between 30 and 40 PSI, pounds per square inch. But in a circuit, we call that the voltage. But all voltage is what we call the push. Okay, voltage is the push. Okay, so a bigger pipe could push out a lot more water. We'll talk about all that as we move through here too. So a simple circuit, okay? This is our cell, our source, whatever you want to call it, our battery in this case, and this is our resistor. That's the simple. This is what we call the schematical drawing, and this is kind of a physical representation of that. Notice the battery or pump has to do work using up some of that energy, what we call a potential, okay? And then that gets here, and then this little resistor is the little wheel that does kind of anti-work to it. That's a simple circuit. It's about as simple as it can get. All right. Again, current is the amount of charge that flows per second. Again, these words flows and per second mean that it is a rate. The symbol for current is I, the variable, shall we say. The charge we know is Q, so the amount of charge per time is that. And then what we say is current is measured in its unit is amps. Okay, its unit is in amps. Okay, and this rate is a coulomb. Okay, remember this rate is a coulomb, so a coulomb per second is amps, which is also current. These are kind of all your symbols, their units, how they're broken down. So this is an old school kind of slide from years and years ago, but this kind of has all the variables and what they are. This is how we kind of convert from American kind of symbols to international IB symbols. And actually, the IB ones are kind of nice. They're very similar. You'll notice, I know it's a little cut off down here, but they're pretty much the same everywhere, except for in a switch in America and in a lot of the labs we're going to do, a switch is kind of this thing right here, and then this can either close to complete the circuit or it can open to break the circuit. While in IB, it kind of looks like a resistor, but they put an S in it. Okay. And then a resistor kind of looks like this jagged kind of looking thing, like it kind of bends in a river, kind of resisting you, versus just a resistor with no label. And sometimes in IB, they'll actually put like 100 ohms on here or 10 ohms or something like that to kind of just label that resistor. So, and you will need to know these. There's a little quick check just to know so that you know them. All right. So electron flow. Electrons, remember, we have a positive and negative thing here. If this was a battery, if we drew a battery right here, anybody know a battery, which sends the end is the negative end on a battery? It has this little like nub out here. Yeah, the part with no nub is the negative, and the part with the nub, if you will, is the positive. So if this was a battery, we just kind of draw a battery here, but we tend to draw this source right here. Electrons flow out of the negative end, and they cause, or what we say is they build the bridge. They have to make this kind of bridge that flows this way so that the current can actually flow the opposite way. Current flows from positive to negative. It flows from positive to negative. And this jump, this potential, is where energy is used inside the battery. These are where the chemicals have to do the work to do this. And this is why eventually you have to replace batteries because of this jump right here. Okay. If it has a bigger potential, for example, if if this was a regular battery that's 1.5 volts, maybe it has this space. If it was a 9-volt battery, we'd move this smaller terminal over here. That'd be a bigger jump. That's why some batteries last longer than others. All right. Sorry, I kind of talked about that. I kind of talked about that ahead of this slide, but this is exactly what we're talking about, making that jump. Okay. We probably won't get into this that much this year, but work right here, the amount of work done is equal to the voltage times the charge. Okay. The amount of work is equivalent to the voltage times the charge. All right. So wires. There's a lot of different wires. I've had kids do this for their IA and everything, but the idea that wires have a lot to do with it. This idea of cross-sectional area, the idea of what type it is, how long it is, how thick it is, all that kind of stuff. And that has a term called resistivity, which we're going to get into. All right. So for example, here, let's try this. If a current flows at 10 amps, okay, so that's our current, that's our I. Okay, that's our I. For 15 seconds, how much charge flows? So for an amp, remember, is 10 per second. Well, it has a flow for 15 seconds. So it's pretty easy. You just do 10 times 15, and we know that 150 charges flew past there in 15 seconds. How much energy is lost when a 5 coulomb charge flows from a positive to a negative? So basically, it's making the jump. What it's saying, it's making that jump to this terminal in a 9-volt battery. Well, what does 9-volt mean? Well, 9-volt means it's literally pushing. It's got it covered up down here. Sorry about this. We got to move this. All right. But what it's saying is 5 coulombs means that for 1 coulomb, it takes 9 joules of energy in a 9-volt battery. So 9 volts means for every 1 coulomb, it had to push 9 times. Well, there's 5 coulombs times 9 joules, or 9 per every 1, and we get 45 joules. Okay, that's why a 9-volt battery can push a lot more. And that's why 9-volt battery is a little bigger, because it needs to push and push and push. All right. Obviously, this is the symbol for resistor. Resistors are measured in something called ohms. Okay, the Lululemon kind of symbol there, the omega. All right, resistivity. Oh, and I love how this is a little jacked up on here. But resistivity, the symbol is this rho, this P right here. Okay, R is resistance. A is the cross-sectional area. So on a circle, if you think of a wire or something like that, our cross-sectional area, that's this area right here. And then it's divided by the length of the wire. So we're going to do this simulation, but let's talk about resistivity real quick. Let me come out here and open this guy up. All right, so for example, if we look at this relationship, now this has substituted the R, the rho, and the R. We flipped them, okay, so that we're kind of looking at resistance, okay? If we increase the resistivity, notice the resistance goes up. So for example, look, what is that doing? The resistivity are all those little particles, or the density within inside the wire. Turn that volume down there. All right, so if there's more particles in the way of the flow, there's more little obstacles, the resistance is going to go up. Well, that makes sense, right? Okay, how about length? All right, if length gets bigger, resistance goes up. Think about it like a road. If I need to cross the road, if it's a longer road and we think of every one of these dots as a pothole, well, there's a bigger chance that I'm going to be resisted more because there's more potholes. Okay? And then finally, area. If the area actually gets bigger, the resistance goes smaller. Again, think of it like a road with potholes. If I have a bigger area to get around those potholes, then what is resisting me is actually going to go down. If the area gets really small and the track gets really small to where I don't have much room and I have to hit all those potholes, and the resistance gets infinitely bigger. And then there's always the relationship of like, well, what if there's more potholes, but I make the road really short? Well, even though there's more potholes in that shorter distance, there's a better chance that we can skip them. Again, if there's more potholes and we make the road longer, there's a better chance of us hitting it. So hopefully you kind of get this understanding of what resistivity is within a circuit. All right, we'll go back over here. Again, just a few more slides. We're going to do this simulation in class together, or not in class together, but you're going to work on it, talking about the flow of electrons through a battery, the relationship of all of that. All right. So what I just showed you on the other thing is how the flow or that of those electrons through there. And that's what you should have discovered in your lab. All right. So again, here's a little example for you. If the resistivity of a copper wire, what is that? What symbol is that? Resistivity. Rho. Very good. What is the resistance of a 1 meter length, L, of a 2 millimeter diameter copper wire? First of all, are we ever in millimeters? You should be screaming, no, Mr. Timo, we are always in meters. So we convert millimeters to meters. That's 0.002 meter diameter copper wire. And this would be our A. Very good. All right. And it wants to know, what is the resistance? Okay. So we're looking for R. R is our question mark, right? R is our question mark. Well, first of all, this isn't our area. Sorry. This is our diameter. Okay, so we have to solve for area, and area of a circle is pi r squared, right? This is diameter, so we have to cut it in half. So this is the r. We do that, and this is now our a. Okay, this is now our a. We use our resistivity equation. We plug and chug, and we get that right there. Not a very big resistance. Not a very big resistance. But if the length would increase, then yeah, we'd have a lot more resistance. So this all comes down to Greg Ohm, Mr. Ohm, Dr. Ohm. Dr. Ohm said, hey, V equals IR. V equals IR. That this is the relationship between voltage, current, and resistance. And we're going to discover that. It is a direct relationship, and we will be working on that. Okay, so we'll be doing that online simulation, and we'll be rocking and rolling. Until next time, Mr. Tima out.